We consider time-invariant systems in the same form and with the same properties as when we define what we mean by Lyapunov stability of equilibrium points. To use Lyapunov's direct method, we need to find a function that can be used instead of energy to determine the stability properties of the equilibrium point. This function is called a Lyapunov function candidate. Candidate because we do not know yet whether it indeed has the necessary properties to serve as a generalized energy function, making it possible to analyze the stability using this function. It is a scalar function, mapping the domain D to a real number, and it has to be continuously differentiable. The derivative of this function along the system trajectories is, as we discussed earlier, the directional derivative of v along the vector field f, and is computed as the gradient of v times the system vector function f, which we clearly see gives a scalar number. The question is, which properties must such a function have in order to actually be used to determine stability of the equilibrium point? This is what Lyapunov answers in the Lyapunov theorems. The function is a Lyapunov function, so no longer just a candidate, if and only if. It is continuously differentiable. As stated before, this is to make sure that v has the continuity that we have based our intuition on. In addition, when x is 0, then v has to be 0. And when x is non-zero, then v has to be strictly positive. We write this as v being strictly positive in D except at the origin. Note that this second criterion is the definition of v being positive definite in D. So why is this second condition, requiring v to be positive definite, necessary? The condition ensures that v has a minimum at the origin. Say that v constantly decreases, then v will become smaller and smaller until it becomes 0, which is its minimum value. And v being 0 means that x is 0, since v is strictly positive anywhere else in D. Later we will see that this condition also implies that the level surfaces are closed near the equilibrium point. The third condition says that the time derivative of v has to be negative semi-definite in D. By the definition of definite and semi-definite functions, this means that when x is 0, then the derivative of v is 0, and it is smaller than or equal to 0 everywhere else in the set D. Why is this important? Because this condition implies that the value of v, this generalized energy function, decreases or is constant along the system trajectories. And note that this last condition is the only condition where the system equations come in. V dot is the directional derivative of v along the vector field, so here the system equations come into the criterion. The previous two conditions only regard the function itself, and the system dynamics do not come in here. If all three conditions are satisfied, then v is a Lyapunov function for the equilibrium point at the origin for the given system. If, moreover, v dot is not only negative semi-definite but negative definite in D, then v is a strict Lyapunov function for the equilibrium point. This condition implies that the value of v, our generalized energy function, steadily decreases along the system trajectories, such that it eventually will end up in its minimum, which by condition 2 occurs at the origin. Lyapunov's stability theorem, which is theorem 4.1 in the book by Khalil, states that If there exists a Lyapunov function for the equilibrium point, then the equilibrium point is stable. This corresponds to the scenario here that we discussed earlier. If there exists a strict Lyapunov function for the equilibrium point, then the equilibrium point is asymptotically stable. This corresponds to the scenario here. So, how do we apply Lyapunov's direct method to analyze the stability properties of an equilibrium point? The first thing we do is to choose our Lyapunov function candidate. That is a function which is our candidate to take the role as a generalized energy function. And this is the challenge of applying Lyapunov's direct method. There is no general way to choose this function. If the system is an electrical or a mechanical system, then it's natural to choose the total energy of the system as our Lyapunov function candidate. Other times we may choose V as a quadratic function in this form here, with a positive definite P matrix. The reason why we have 1/2 as a coefficient is that the coefficient then disappears when we later take the derivative. And we may try the particular case where the P matrix is diagonal, resulting in this Lyapunov function candidate. Also, there exist some methods for choosing the Lyapunov function candidate, and we will get back to this later. When we have chosen our Lyapunov function candidate, the next thing we do is that we determine whether the function is indeed a Lyapunov function, or preferably a strict Lyapunov function for the equilibrium point. This is done by checking whether the conditions in the definition of a Lyapunov function are satisfied. If the answer is yes, then Lyapunov's stability theorem gives that the equilibrium point is stable in the case when V is a Lyapunov function, and that it is asymptotically stable in the case when V is a strict Lyapunov function. What if the answer is no then? What if the function we have chosen as our candidate turns out not to be a Lyapunov function? Then this only means just that. This candidate was not a Lyapunov function, and we must start over again, choosing another Lyapunov function candidate and check whether this new one satisfies the conditions to be a Lyapunov function. So that the Lyapunov function candidate is not a Lyapunov function does not mean that the equilibrium point is unstable. Specifically, note that the conditions in Lyapunov's stability theorem are sufficient conditions. They are not necessary conditions. There do exist instability theorems for establishing that an equilibrium point is unstable. The most powerful of these theorems is Pettersen's theorem, which is theorem 4.3 in the book by Khalil. This is a theorem which is interesting to read and know about, but since we generally do not want to design our control systems to be unstable, Pettersen's instability theorem is not a central part of this course. Let us look at an example to illustrate how to apply Lyapunov's direct method. Let us consider the pendulum again, both with and without friction, and normalizing the mass to 1. From previous analysis, we know that both systems have an equilibrium point at the origin, and we will now use Lyapunov's direct method to analyze the stability properties of this equilibrium point. First, consider the case without friction. The first step is to choose the Lyapunov function candidate. Since this is a mechanical system, it is natural to try using the energy as Lyapunov function. So our Lyapunov function candidate is V of x equals the potential energy plus the kinetic energy. From physics, we know that the potential energy is minus the integral of the conservative force acting on the system, which here is the gravitation force. So the potential energy is minus the integral from 0 to x1 of the potential force, which here is minus g over L times sine y. When integrating, we here use y for the rotational displacement, so sine of y dy. The kinetic energy is 1/2 times the mass, which is 1, times the velocity squared, that is x2 squared. And computing the integral, this is g over L times 1 minus cosine of x1 and plus 1/2 x2 squared. This is our Lyapunov function candidate. How do the level curves look like for this Lyapunov function candidate? I have here normalized the equation by setting g over L to 1, and I've used the MATLAB function f-contour to generate the level curves. Each color corresponds to a certain constant value of the energy function v of x, with 0 energy at the origin and increasing levels of energy as we move outwards. At a certain energy level, we see that the level curves are no longer closed curves. We can also illustrate the chosen Lyapunov function candidate by a surface plot, using for instance the function EasyMeshC in MATLAB. Then we have the actual value of v along this axis. And projecting the value of v into the x1, x2 plane and using color coding, we see that we get the level curves from the previous plot. We see that the function has a local minimum at the origin, but it also has minima when the angle x1 is plus 2 pi or minus 2 pi, with the angular velocity x2 being 0. After choosing our Lyapunov function candidate, the second step is to determine whether our candidate is a Lyapunov function, or preferably a strict Lyapunov function for the equilibrium point at the origin, by checking whether it satisfies the conditions in the definition. Our Lyapunov function candidate consists of a constant, a cosine term, and a polynomial term. These are all continuous, so the v function is continuous, and its time derivative exists and is continuous. So our candidate is a continuously differentiable function. Is it positive definite? Well, v evaluated at the origin is clearly 0, because cosine of 0 is 1, so we get 1 minus 1, which is 0, and also the second term is 0 at the origin. Is it strictly positive everywhere else in the state space? No, it is not, because the first term is 0 also other places in the state space, for instance if x1 is 2 pi or minus 2 pi. We notice that already here, that the energy function has several local minima. So does that mean that this is not a Lyapunov function? Well, it is not a Lyapunov function for the origin in the whole state space, but that is not necessary either. We only need it to be strictly positive in some domain D around the origin. As long as we choose this domain to not include the other local minima, everything is fine. So if we choose the domain D as all the states in R2, such that the absolute value of x1 is strictly less than 2 pi, then the function v is strictly positive everywhere in the domain D except at the origin, where it is 0 as it should be. So in this domain D, the function v is positive definite. So the second condition is satisfied. How about the third condition? Until now, we have only considered the function v, and it's only in the third condition that the system equations come into play. We will now see how the function v evolves along the system trajectories by computing the directional derivative of v along the vector field f. The time derivative of v is the derivative of v with respect to x1 times the time derivative of x1 plus the derivative of v with respect to x2 times the time derivative of x2. The derivative of v with respect to x1 is g over L times sine x1. And the derivative of x1 is x2 by the system equations. Plus the derivative of v with respect to x2, which is x2, times the time derivative of x2, which is minus g over L sine x1, according to the system equations. And we see that this is 0. So the time derivative of v, which is the directional derivative of v along the trajectories of the system, is 0, which makes sense since this is a conservative system. This holds for all values of x. So this does not require a further restriction on the domain D. In other cases, we could here have to restrict the domain D further to obtain a domain where all three conditions are satisfied. So our Lyapunov function candidate V is defined on the domain of all states in R2, such that the absolute value of x1 is less than 2 pi, and it maps this domain to a scalar number. And on this domain, it satisfies all the conditions to be a Lyapunov function for the equilibrium point at the origin. It is not a strict Lyapunov function though, since the derivative is 0 everywhere and not only at the origin. One question that I often get is, but how can the derivative be 0 when the surface plot clearly shows a wave-like behavior? What we see here is how v varies with x. So the derivative of v with respect to x is not 0, but this is not what we calculate when using Lyapunov's direct method. What we calculate then is the time derivative of v, which gives how v varies with time along the system trajectories. For the pendulum without friction, we remember from the phase portrait that the system trajectories are closed orbits about the origin. That the directional derivative of v along f is 0 means that along these closed orbits, the energy level does not change. So the energy level is constant along the system trajectories, meaning that the trajectories follow the level surfaces. How do the trajectories intersect the level surfaces when there is friction in the system then? Because the friction force acts on the system, it is no longer a conservative system. Friction is a dissipative force, which draws energy from the system. From the phase portrait we created in a previous lecture, we already know that the origin is locally asymptotically stable. But let us see how this can be analyzed using Lyapunov's direct method. Again, we use the total energy as our Lyapunov function candidate. The properties of the function are the same regardless of the system, so this is still a continuously differentiable function, and it is positive definite in the domain D, consisting of all two-dimensional vectors for which the absolute value of x1 is strictly less than 2 pi. The change of system equations only affect the third condition, the one that concerns the derivative of v. The time derivative of v is the derivative of v with respect to x1, which is g over L sine x1, times the time derivative of x1, which is x2 by the system equations, plus the derivative of v with respect to x2, which is x2, times the time derivative of x2, which by the system equation is minus g over L sine x1 minus k over m, but m is 1, so k times x2. This term here cancels this term, and the result is minus k times x2 squared. Now I want you to pause the video and decide whether v is a Lyapunov function or a strict Lyapunov function for the origin of the pendulum with friction. Specifically, since the two first conditions are satisfied, I want you to decide whether the derivative of v is negative semi-definite or negative definite. To repeat what we mean by negative semi-definite and negative definite, the function v dot is negative semi-definite in a domain D about the origin if it is 0 at the origin and it is less than or equal to 0 in every other state in the domain. And it is negative definite in a domain D if it is 0 at the origin and it is strictly negative for all other states in the domain except the origin. The derivative of v in this case is minus k times x2 squared. It is clear that when x is 0, then v dot is 0. The domain that we have been considering so far is this one. This could be further restricted to make sure that this third condition on v dot is satisfied, but for now let us consider this domain. Is v dot strictly negative everywhere in D except at the origin? No, it's not. V dot evaluated in any state where x2 is 0 will be 0, regardless of the value of x1. So v dot is 0 along the whole x1 axis. So v dot is 0 for all the states along the x1 axis. As mentioned earlier, we can at this stage further restrict the domain D, which we found when evaluating the second condition, to a domain where also the third condition is satisfied. But in this case, we're not able to find any domain about the origin where v dot is negative definite, because regardless of how small we make this domain about the origin, the x1 axis will always be part of the domain. So v dot is negative semi-definite in the domain D. So v satisfies all the conditions to be a Lyapunov function, and by Lyapunov's stability theorem, we know that the origin is stable. We know from the phase portrait that we created for this system that the origin actually has a stronger stability property. It is locally asymptotically stable. But this choice of Lyapunov function candidate only proves stability. If we want to prove asymptotic stability, we need to try another Lyapunov function candidate, and this you will do in one of the course assignments. Alternatively, you may use a theorem called the invariant set theorem or Lassalle's theorem, which you will learn later in this course, to show asymptotic stability even if the Lyapunov function is not a strict Lyapunov function. But more about this later. For now, if you want to use Lyapunov's stability theorem, which is theorem 4.1 in the book, to show asymptotic stability, you need to choose another Lyapunov function candidate.